Welcome to the deep dive. We've received a stack of sources from you, some truly wonderful, curious material, and our mission is to take a deep dive, extracting the most important nugget of knowledge buried within.
Hmm.
Think of this as your shortcut to being well informed on a truly unique topic.
And today, that topic is, well, it's a deep dive into logic, mathematics, problem solving, all wrapped up in these whimsical stories. Penned by an author you definitely know.
That's right, we're unpacking excerpts from A Tangled Tale, a collection of short stories, or knots as he called them, written by none other than Lewis Carroll.
Yeah, Lewis Carroll. But this is, it's far from simple fiction. Each knot cleverly contains a mathematical or logical puzzle woven right into the narrative.
Right, into the story itself.
And Carroll's genius here, it's his approach. He embeds these, quite challenging problems within wonderfully eccentric scenes, character interactions. But the real value, and what makes this source so rich for us, for Deep Dive, is the detailed commentary that follows each knot. He dissects reader attempts, highlights the surprisingly common errors, and meticulously explains the correct solutions. It's quite something.
So our goal today is to follow Carroll's lead, really. We're going to explore some of these specific knots, understand the puzzles, appreciate the cleverness.
Both the challenges and the solutions.
Exactly. And crucially, learn from the common pitfalls readers stumbled into, often in, well, quite funny ways sometimes. It's all sourced directly from the text you shared.
Let's pull on these tangled threads then and see what we find.
Okay, let's unpack this first one. Knot I, Excelsior. The scene is wonderfully vivid, isn't it? Sunset, a mountain.
Yeah?
Two travelers, a young, agile one, and an aged, weary companion weighed down by heavy chain armor.
Right. Chain armor, because obviously that's standard hiking gear.
Completely normal for a mountain walk.
Absolutely essential. So they're descending quite quickly, actually, at 6 miles an hour. They went up at a slower 3 miles an hour.
And their pace on the level ground is 4 miles an hour.
Right. And the entire journey, up and back, it starts at 3 in the afternoon and finishes by 9 in the evening.
So that gives them precisely 6 hours.
6 hours, yep.
The younger traveler, full of energy, full of questions, wants to know the total distance they walked, and more specifically, what time they actually reached the peak of the mountain.
Right.
But the elder knight may be a bit tired of conversation under all that armor.
Understandable.
He sets a condition, guess the pick time within half an hour, and then he'll reveal the total distance.
Now here's where the puzzle truly begins, and where the commentary offers the first big aha moment.
Okay.
The commentary revealed a key insight right away. The total distance they walked the round trip, out and back, is a fixed 24 miles.
Wait, 24 miles? Fixed? How can the total distance be a fixed number, regardless of how much of the path was level or uphill or downhill? That seems wrong.
It really does, doesn't it? But the commentary explains it beautifully by focusing on the time taken.
Okay, the time.
Think about traversing 1 mile uphill and then descending that same mile. Going up at 3 mile an hour takes, what, 13 of an hour?
20 minutes. Right.
Coming down at 6 mile an hour takes 16 of an hour.
10 minutes.
So the total time for the uphill-downhill pair is 13 plus 16, which equals 12 an hour. 30 minutes.
Okay, half an hour for 1 mile up and down.
Now, consider walking 2 miles on the level. At 4 mile an hour, each mile takes 14 of an hour, 15 minutes.
Right.
So 2 miles on the level takes 14 plus 14, which is also 12 an hour.
I see. So going up and then down any given mile takes the exact same total time as walking 2 miles on the level at their speeds.
Exactly. Over a 6-hour round trip, the total time spent on any combined uphill-downhill sections is effectively equivalent in terms of distance covered relative to time to walking twice that distance on level ground at 4 mile an hour. So the 6 hours is mathematically like walking for 6 hours straight on level ground at 4 mile an hour.
6 hours times 4 mile an hour, 24 miles, 12 out, 12 back.
Yep. The total distance is indeed 24 miles, no matter the terrain breakdown.
That is a really neat bit of logic. Cleverly hidden. It makes you rethink how you calculate journey times.
It does. But what's truly fascinating, and where many readers got tripped up according to Carroll's commentary, is that while the distance is fixed at 24 miles, the time they reach the peak, well, that cannot be precisely determined from the information given.
Really? The commentary says it could be any time between 6 o'clock and 7 o'clock. Why isn't it a single time if the speeds and total time are fixed?
Because the relationship between the time spent on level ground during the ascent and the time spent on level ground during the descent, well, it's linked. But the specific amount of level ground traveled on the way up versus on the way down isn't defined.
Ah.
And this leads to what's called an indeterminate equation when you try to solve for the time spent ascending, which in turn defines the peak time.
So you can find a range of possible peak times that fit the 6-hour total.
Exactly. A range between 6 p.m. and 7 p.m. works, but not one single answer.
That's surprising. And a valuable lesson right away. Not all well-defined problems with numbers necessarily give you a single specific answer. Some only give you range. Or maybe they're impossible with the given data.
Precisely. And the commentary, it has some fun dissecting the common errors. Carroll points out readers like Gertie Vernon, who just assumed specific distances for the different terrains, information that just wasn't provided.
Right, making stuff up.
Others, like someone called a nihilist, made basic errors in arithmetic, or they incorrectly tried to average speeds, which is a common trap.
Yeah, you can't just average speeds like that.
Agnes Bailey assumed they spent the same amount of time on the level as uphill. Again, totally unfounded in the text.
And Fifey mistook the rate on the level, the 4 borough, for the actual distance walked on the level, which the commentary humorously calls a cell, quite beneath the dignity of the elder knight.
Quite right. Carroll doesn't just point out errors, though. He praises those who got it right. He highlights readers like Marlborough Boy and Putney Walker for spotting the indeterminate nature of the peak time. They used algebraic solutions.
Nice.
And you even get delightful poetic solutions from readers like Blythe, like, on hill and plain, twixt 3 and 9, the miles were 24.
Ha! Love it. This knot really teaches us the importance of understanding the underlying principles, like that time equivalence thing, and being aware that not every variable might be solvable, even if others are, recognizing indeterminacy.
Right. So from mountain peaks, let's descend into the curious world of continuous loop railways and eccentric relatives.
Ah, yes. That brings us to Not the Third, where we meet the memorable Mad Mathesis.
The eccentric stance.
She's introduced as someone who deliberately avoids everything conventional. No long dresses, no lawn tennis.
Can't cook, can't set a bone.
Definitely not. She's a wonderful contrast to her niece, Clara. Clara is utterly bound by the strict rules of her excellent preceptress, which include prohibitions on things like betting and, crucially for later, puns. No puns allowed.
A fascinating pair. So Mad Mathesis takes Clara to London and describes this new continuous loop railway line. It runs from London to the border of Wales, touches at York, goes down the east coast, and returns to London. A full loop.
Okay. And the journey time for a westerly train is 2 hours.
While an easterly one takes 3 hours.
And trains start both ways every 15 minutes on the dot from Charing Cross.
Got it.
And here's the puzzle Mad Mathesis poses. If she takes a train going west and Clara takes one going east, each traveling the full loop, how many trains does each traveler meet on their journey? And then a twist. How many do they meet if they only count the train containing the other traveler?
Okay, this puzzle is a classic. It involves relative speed and understanding the timing and frequency of objects moving on a loop.
Right.
Carroll's commentary, in explaining the solution, uses these abstract units for the railway's length, based on the least common multiple of the journey times.
2 and 3 hours. So
Yeah.
6 hours or 360 minutes.
Exactly. He divides the railway into 360 units. This gives the westerly trains a speed of 3 units per minute,
360 units divided by 120 minutes. Yeah.
and easterly trains a speed of 2 units per minute.
360 divided by 180 minutes. Got it.
And trains start every 15 minutes, so they are spaced out at intervals corresponding to 15 minutes of travel time for their direction.
Okay, using the units helps standardize things, so they're constantly passing or meeting other trains going the opposite way.
Exactly. Because they are on a loop, they meet trains that started before them and trains that started after them.
Right.
For the first part of the question, meeting any train going the other way, the commentary confirms that each traveler going around the entire loop will meet 19 trains.
19. And the commentary explains this how. It mentions meeting points.
Yes, as the trains meet at fixed points around the loop, 18 units apart. This creates 20 sections and therefore 19 meeting points or posts. Going around the loop means you pass all 19 points.
Ah, okay. That seems straightforward once you visualize the loop and the meeting points.
It is. The trickier part is the second question. Only counting the train carrying the other person.
Right, the specific train with Clara or Mathesis on it.
The commentary states they meet that specific train 72 minutes into their respective journeys. The question then becomes, how many trains like that specific one carrying the other person started every 15 minutes does each traveler encounter over their entire journey?
Okay. And the commentary gives the answers. The easterly traveler, Clara, meets 12 such trains.
Yep.
And the westerly traveler, Mad Mathesis, meets 8. But how do you get those numbers? The commentary mentions something about the easterly traveler counting trains within a 5-hour window relative to their position. What does that mean?
Right. The core idea is that during their journey, they encounter trains going the other way that started at various times before them. The number you meet depends on your journey time and the frequency of the other trains. So over the 3-hour easterly journey, Clara encounters all the western trains that started within a certain time window relative to her start. The commentary's detailed calculation, using those units and relative speeds, leads to her meeting 12 trains.
And Mathesis, on her faster 2-hour journey, encounters fewer, only 8.
Exactly. It's about counting how many of the other person's trains they intercept over their total travel time.
That's much clearer. It's not just about passing static points, but about dynamic interception based on timing and speed. Makes sense.
And the commentary calls out a very common mistake here, the Clara theory.
The Clara theory. What's that?
This often involved miscounting trains met right at the start or end of the journey. Specifically, incorrectly excluding the train met just before arriving back at the terminus.
Ah, so they thought if you met it just seconds before finishing, it didn't count.
Precisely. Carroll corrects readers like B.O. Peep, emphasizing that if a train is met before you reach the final stop, it absolutely counts. It highlights how crucial precise definitions are in these puzzles. When does the journey end?
It certainly does. It's a good reminder that the boundaries and conditions of a problem matter immensely. Don't ignore the edges.
Right. So from railway loops, we sail off to Kingavieni. Still tricky to say. For 5 bags.
Okay.
To find ourselves on a ship. Fishermen are attempting to weigh sacks of money using rather unconventional weights, like winch handles and belaying pins.
Huh. Yeah, a recipe for inaccuracy if ever there was one. The trouble really starts when their 5 money bags are accidentally knocked overboard.
Oh dear.
The captain, described as a man of principle and immense pride in my ship, decides he must compensate the fishermen.
A very honorable captain, if maybe a bit proud. But he's got a problem. The fishermen can't tell him the individual weight of each of the 5 sacks.
Right.
All they have are the results of their makeshift weighings, which were of the bags combined in specific pairs, and 1 triplet.
So the captain is presented with this list of combined weights. Let's see.
Okay.
Sack 1 plus sack 2 equals 12 pounds.
Got it.
Sack 2 plus sack 3 equals 13.5 pounds.
13 and a half. Okay.
Sack 3 plus sack 4 equals 11.5 pounds.
11 and a half.
Sack 4 plus sack 5 equals 8 pounds.
8.
And using a large hammer as a counterweight, sack 1 plus sack 3 plus sack 5 equals 16 pounds.
16 pounds. Okay. And the captain's dilemma, which he confesses, it beats me entirely, is how to figure out the weight of each individual sack from these combined totals.
Yeah, the younger traveler just throws up his hand, says if they didn't weigh them separately, you just can't know. But the elder traveler, he knows better.
It certainly looks like a puzzle where you have multiple unknowns, the weight of each sack, and multiple pieces of information connecting them.
That's exactly what it is. This is a classic example of a system of linear equations.
Algebra time.
Pretty much. While it can be solved through careful substitution and arithmetic, the commentary points out that many readers tried guessing or made wild, faulty assumptions.
Not quite.
Well, Carroll humorously debunks the idea that if 3 out of 5 sacks in a group weigh 16 pounds, then they must somehow represent 35 of the total weight of all 5 sacks combined in other ways. Logic he rightly calls baffling.
Yeah, that doesn't make any sense at all. Guessing seems like a risky strategy for a captain trying to be fair.
It is. The commentary praises those who used algebraic methods. Think about it. You have 5 sacks, so 5 unknown weights. Let's call them S1, S2, S3, S4, S5.
Okay.
You have 5 equations linking these unknowns based on the given weights. For example, S1 plus S2 equals 12, S2 plus S3 equals 13.5, and so on, including S1 plus S3 plus S5 equals 16.
Right, 5 equations, 5 unknowns.
Yeah.
Solvable, usually.
Exactly. The approach is to use these equations to isolate one variable at a time. If you know S1 plus S2 equals 12, then S1 must equal 12 minus S2.
Okay.
You can then substitute that expression for S1 into another equation that involves S1, like the S1 plus S3 plus S5 equals 16.1. That reduces the number of unknowns in that equation.
So it's about systematically substituting and combining equations.
Yep. Until you can narrow it down and find a specific value for one sack, and then you can work backwards or forwards using that known value to find the others.
Got it. It highlights the power of a systematic approach like algebra over just trial and error or guesswork, especially for problems with multiple interconnected variables. Very neat.
Our next stop is back in Governey for Notsa 6, Her Radiancy. We're introduced to Her Radiancy, a plump little damsel, a few words. The governor, Norman, and our elder traveler again. Their guests and their entertainment. Solve a puzzle or face the Imperial Dungeon.
A rather high-stakes game night.
Definitely. The main puzzle here is a scarf-making competition between 3 candidates. Lolo, Mimi, and Zuzu. They're judged on 3 qualities: speed, lightness, and warmth.
Okay.
And the problem provides specific ratios comparing them on each quality.
All right, let's hear them.
For speed, Lolo makes 5 while Mimi makes 2. Zuzu makes 4 while Lolo makes 3.
Okay, ratios.
For lightness, which is inversely proportional to weight, so lighter is better, 5 of Zuzu's scarves weigh the same as one of Lolo's, and 5 of Mimi's weigh the same as one of Zuzu's.
So Lolo's are heaviest, Mimi's lightest.
Looks like it. And for warmth, Lolo is twice as warm as Mimi. Zuzu is twice as warm as Lolo.
So Zuzu is warmest, Mimi least warm.
Right. The Imperial competitions give a maximum mark of 10 for the best in each quality. The question, who is the best overall candidate?
Okay. The core mathematical challenge, where the commentary spends significant time, is how do you combine scores or qualities when they're given as proportions like this? How do you figure out who is best overall?
And the commentary highlights a massive common error.
Let me guess. Adding.
Exactly. Adding the proportional numbers for each candidate instead of multiplying them to get an overall score.
This is such a critical and often missed point. Carroll uses a brilliant analogy in the commentary to explain why you must multiply.
The tank digging one.
That's the one. Imagine you're judging diggers of rectangular tanks based on 3 qualities: length, width, and depth. Okay? If one digger is twice as good at length, another twice as good at width, and a third twice as good at depth, their overall excellence isn't the sum of those multipliers. The total amount of work, the volume, is calculated by length times width times depth.
Ah, right. Volume is multiplicative.
Exactly. So if you're assessing overall quality, which is a product of several independent qualities, you must multiply their relative scores, not add them.
That analogy makes it perfectly clear. The overall result is a product of the factors, not a sum. The commentary calls out many readers who made this adding error, the 24 malefactors.
He also dissects other faulty reasoning, like some people assumed warmth was a bad thing and a demerit, or they use entirely nonsensical methods to compare candidates, which led some to incorrectly pick Mimi as the best.
Mimi, but she seemed weaker on a couple of fronts.
Right. Carroll even pokes fun at Belbius, a character from Another Knot We'll Meet, for his slightly convoluted attempt to explain why multiplication is right, humorously comparing his flawed logic to concluding this is not spring, therefore it must be autumn.
Huh. Classic Carroll. The commentary also briefly touches on another, smaller riddle embedded in the text, the merchant riddle.
Oh, yeah.
A friend and his brother each started the year with 1,000 pounds. On New Year's Day of the following year, they had 60,000 pounds between them.
Wow. Good year.
Having borrowed naught and stolen naught.
Ah, not. This is less a math problem and more a language puzzle, right?
Exactly. The solution hinges on interpreting not just as nothing, but as the digit 0.
Right, so you apply the 0 cleverly.
The commentary mentions solutions involved, applying the 0 digit to the original numbers, like changing 1,000 pounds to 100,000 pounds by adding zeros, or even changing digits using the 0 concept somehow, like turning the 1 into a 6 or a 9.
Very clever wordplay. It's a lateral thinking puzzle. This knot, particularly the scarf competition scoring, is a powerful lesson in choosing the correct mathematical operation to model a problem. Multiply for combining proportional qualities, don't add.
And the merchant riddle reminds us that sometimes the answer lies in reinterpreting the language itself.
Speaking of Balbus, we revisit him and his pupils, Hugh and Lambert, in Knot 9X. Balbus is presented as someone who can get completely lost in theoretical problems.
Oh, yes.
And we see this vividly in his essay on displacement.
The infamous essay where Balbus contemplates Archimedes' principle. He pictures plunging a solid cylinder into a jar of water.
Right.
He observes that as the solid goes in, the water level rises. Okay, makes sense.
But then this higher level immerses a little bit more of the solid,
Which causes the water to rise further.
which immerses even more of the solid, and so on and so on.
Yeah, you can see where he's going with this step-by-step logic.
Balbus, following this logic, comes to a rather dramatic and incorrect conclusion. He states this process must continue indefinitely until the entire solid is immersed,
Okay.
and then the water will start to immerse whatever is holding the solid.
Oh, dear.
His final, rather dire thought is that if you hold a stick in a tumbler of water long enough, you must eventually be immersed. He even morbidly calls those who perish this way martyrs of science.
That step-by-step logic sounds compelling on the surface. Each rise causes another small rise, but it leads to a completely absurd outcome. You don't drown from holding a stick in water.
Exactly. And the commentary reveals the fallacy. This is a classic application of the concept behind Zeno's paradox.
Ah, like Achilles and the tortoise.
Sort of, yeah. Applied to a converging infinite series. While the water level does rise by an infinite series of decreasing distances in his example, 2 inches, then 1 inch, then 12 inches, then 14 inches, and so on.
Right, the amounts get smaller and smaller.
The sum of that infinite series converges to a finite value.
So even though there are infinitely many steps of the water level rising, the total amount it rises adds up to a fixed number.
Precisely. In his example of 2, 1, 12, 14, the total rise will never exceed 4 inches, no matter how many tiny increments you add.
Ah, okay.
Balbus's error was assuming that because there's an infinite number of additions, the tiny rises, the total sum must also be infinite, which isn't true for converging series.
Right. The commentary praises readers like Old King Cole and Vindex for correctly identifying this as a converging geometrical progression or a Zeno-like fallacy.
It's a fantastic illustration that an infinite process doesn't necessarily lead to an infinite result, a key concept.
Not Nye also includes the garden problem. This puzzle involves an oblong flower garden.
Okay.
That's exactly half a yard longer than it is wide. The entire area is taken up by a gravel walk 1 yard wide that winds inward spirally, filling the whole garden.
A spiral walk filling the whole oblong garden.
Got it. And the crucial piece of information provided is the length of the walk, measured along the very center of the path to its bitter end. Exactly 2 miles and half a furlong.
2 miles and half a furlong, which the text helpfully converts to 630 yards.
Right. 630 yards long. The challenge is to find the dimensions of the garden itself, length and width.
This problem links the length of a path to the area it occupies, given its width and shape. It sounds complicated because of the spiral.
It does seem tricky, and the commentary highlights common errors that arose from misinterpreting the geometry.
Like what?
Some readers made incorrect assumptions, like thinking the length of the path was related to the square root of the area, completely ignoring the path's width.
Just using the length and ignoring the width.
Others struggled with the spiral shape or simply made arithmetic errors. Carroll calls out someone named 2mm Panem for particularly bad assumptions, including contradicting the problem by assuming the walk didn't use the whole area.
Yikes. How do you even approach a spiral like that mathematically?
Well, the commentary praises Vindex's neat solution method, which simplifies the complexity beautifully.
Oh, yeah.
The key insight is realizing that a section of the walk, 1 yard long measured along its center line, and 1 yard wide, well, it occupies exactly 1 square yard of the garden's area.
Okay.
And this is true whether that section is straight or curved around a corner. Because the walk is 1 yard wide and winds through the entire garden, the total area of the garden in square yards must be exactly equal to the total length of the walk in yards, measured along the center line.
So if the walk is 300 and 630 yards long, and it's 1 yard wide filling the whole space, the garden's area must be 300 and 630 square yards, is that right?
Exactly. That's the leap. And you also know the garden is oblong and half a yard longer than it is wide.
Okay, so if the width is W, the length is W plus 0.5.
Right. And the area is length times width. So W plus 0.5 times W equals 3,630.
Which gives you a quadratic equation to solve for W.
Yep. And the commentary gives the dimensions as 60 yards by 60.5 yards.
Because 60 times 60.5 is 330.
Wow. That's a beautiful simplification. It turns a complex geometry problem involving a spiral into a simple area calculation and a basic equation. It really reinforces that finding the right interpretation or equivalence is often the key.
Absolutely brilliant. Okay, finally, let's look at Not X, the Chelsea pensioners. Clara and Mad Mathesis are visiting these veterans who have sadly lost limbs or senses.
Yeah, Clara is understandably sad about the situation, and she's wary, knowing Mad Mathesis is probably about to hit her with a calculation based on their ailment.
As she does. The puzzle is this. Given the percentages of pensioners who have lost a specific body part, 70% lost an eye, 75% lost an ear, 80% lost an arm, and 85% lost a leg.
Grim statistics.
Indeed. The question is, based only on these numbers, what is the minimum percentage of pensioners who must have lost all four?
The minimum who lost an eye, an D an ear, an D an arm, and D a leg. Wow. That sounds like a tricky logic problem about overlaps. set theory, maybe?
It is, fundamentally, and it requires careful logical deduction. The commentary presents a very clear method attributed to a reader named Polar Star. The key is to flip your perspective.
Flip the perspective, how?
Instead of thinking about who lost what, think about who didn't lose what.
Okay, so if 70% lost an eye, what does that tell us about the others?
It tells us that at most 30% didn't lose an eye, meaning they still have at least one eye, possibly both. We can't assume they do have both, just that they didn't lose an eye in the way the problem counts it.
Okay, at most 30% didn't lose an eye.
Similarly, if 75% lost an ear, at most 25% didn't lose an ear. If 80% lost an arm, at most 20% didn't lose an arm. And if 85% lost a leg, at most 15% didn't lose a leg.
So the maximum percentages of pensioners who still have at least one of each of those things are 30%, 25%, 20%, and 15% respectively.
Right. Now consider the group of pensioners who didn't lose at least one of the four items, meaning they kept an eye, or an ear, or an arm, or a leg, or some combination. What's the maximum possible size of this group?
Would you add those maximum percentages together?
Exactly. The maximum number who avoided losing something is the sum of the maximums who didn't lose each specific thing. 30% plus 25% plus 20% plus 15%. That equals 90%.
Okay, so at most 90% of the pensioners still have at least one of those four things intact: an eye, an ear, an arm, or a leg.
Precisely. And if you still have at least one of them, you cannot be in the group who lost all four.
Right. Right, if you have an eye, you haven't lost all four.
Therefore, if at most 90% don't lack all four items, the remaining percentage must be the minimum percentage who do lack all four.
So 100% minus that maximum 90% gives you 10%. At least 10% of the pensioners must have lost all four: an eye, an ear, an arm, and a leg. The minimum is 10%.
Correct. That's the logic. And the commentary highlights a very specific, common, and crucial logical error here.
What was the common mistake?
Many readers incorrectly assumed that because 70% lost an eye, the remaining 30% must have both eyes.
Assuming perfection in the remainder.
Exactly. Carroll uses a clever analogy. If you find 70 bad sovereigns, old coins, in a bag of 100, you can't assume the remaining 30 are good unless you've actually tested them. You only know that at most 30 might be good.
Right.
Applying that faulty assumption that the 30% must have both eyes, that 25% must have both ears, etc., leads to incorrect results for the minimum overlap.
That's a critical distinction. It's the difference between at most 30% are okay and exactly 30% are okay. The lack of information about the 30% doesn't give you license to assume they are perfect. These examples from the commentary really show how easily logical flaws creep into our thinking, even in simple-sounding problems.
They certainly do. It's quite humbling sometimes.
Well, we've journeyed quite a bit, haven't we? From mountain slopes and continuous railways,
The sinking ships.
imperial dungeons, spiraling gardens, and poignant encounters with veterans. This deep dive into a tangled tale really shows us that math and logic aren't confined to textbooks. They're woven into stories, characters, unexpected scenarios.
Yeah, we've extracted some genuinely valuable insights, I think. We saw the importance of finding those underlying principles that simplify complexity, like why ascending to descending a mile takes the same time as 2 level miles.
Right. And we learned to recognize problems that might lead to indeterminate solutions, where you get a range instead of just a single number, like the peak time.
And we saw the power of choosing the right analytical approach. Setting up equations for the money bags, understanding converging infinite series for Balbus's paradox.
Recognizing that combining proportional qualities requires multiplication, not addition, for the scarves.
And using that logical deduction, thinking about the opposite case for the Chelsea pensioners.
Just as importantly, we learned from the frequent pitfalls Carroll's raiders encountered, all meticulously documented in his commentary, making unwarranted assumptions.
Like in the pensioner's problem, or not I.
Using the wrong mathematical operation entirely, like adding instead of multiplying in the scarf competition.
Or just failing to grasp fundamental concepts, like how infinite series can converge to a finite sum.
These notes are a fantastic reminder that problem solving, whether it's a mathematical puzzle like these or a real-world challenge you're facing, requires careful thinking, a willingness to question your initial assumptions, and sometimes looking at the problem from a completely different angle. Clarity in both your thinking and your definitions is absolutely crucial.
It really makes you wonder. The source vividly showed us how easily common assumptions, even ones that seem logical at first glance, like that Clara theory about train counting, or the fallacy in the Chelsea pensioners problem.
Yeah, they seem reasonable until you poke them.
Exactly.
Yeah.
How easily those assumptions can lead you down the wrong path and result in completely incorrect conclusions.
Right. If relatively simple logic and math puzzles can expose these kinds of flaws in our reasoning.
What other areas of life might benefit from us pausing, just like Carroll's commentary forces his readers to, and really questioning our fundamental assumptions before we jump to conclusions or accept information at face value?
That's certainly something to ponder.